they have these rules. The textbook has these rules for estimation, uh, which are basically just uh, just a second, let me pull this up. Zoom is being kind of laggy today. Are basically just strategies that you use when estimating a value. So you can get big lengths from smaller lengths, or you can get smaller lengths from big lengths. So what this means is, if you know how tall a single story is, then you can multiply by the number of floors in a building to get an estimate of how tall the building is. Or if you know how thick a ream of paper is, then you can divide by the number of pieces of paper in the ream in order to get the thickness of a single sheet. You can get areas and volumes from the lengths, which is, I don't think, even like an estimation trick. I think that's just how you find unit areas and volumes, and you can also get masses from volumes and densities, where density is equal to mass per volume, which is equal to mass per length cubed. And then if all else fails, bound it. So bounding it means that you find a boundary condition. So if you know that if you know that nothing's going to be bigger, if you're estimating the volume and you know that none of the lengths are, it's roughly rectangular and none of the lengths are going to be bigger than 20 feet, then you know that the maximum value that the volume can have is 20 feet by 20 feet by 20 feet. So that is going to be a boundary that you can use when estimating. 1 sig fig is fine. Oh yeah, I didn't really talk about significant figures, but when you're doing dimensional analysis, or not dimensional analysis, that's what we just did. When you're doing scientific notation, the number of figures up front is going to be your number of significant figures. So in this case, we have 1 digit, so this has 1 significant figure. And in this case, we have 3 digits, so it has 3 significant figures. So if you're estimating, then you probably don't need to know more than 1 significant figure, because all of the math that you're doing is so haphazard anyways that it doesn't really matter, because you're just doing estimations. And then when you get to the end of the question, it asks yourself, does this make any sense? Does this have the right units? Does this is the mass that you're getting for the Earth bigger than the mass of the sun? In that case, it wouldn't make sense, so you would have to redo your estimation. So just ask yourself like common sanity checks when you do the estimation. So, sorry, I've been talking for a while and my throat's kind of parched. The book has a problem, oh, nope, don't delete that. Oh, guess I just have to keep that bracket. The book has a problem where it's asking you to estimate the total mass of the oceans on the Earth. So what it needs to, so this is actually a pretty interesting problem because it uses a lot of these methods in order to get it. So get masses from volumes and densities. So you're trying to find the mass of the Earth. So you know that mass is equal to density times the volume. And then we know that the density of water is 10 to the third kilograms per meter cubed. So from this, we can find the mass by knowing the density, which we do, times the volume of the Earth's oceans. And then what this means is that we just need to get the volume in order to get the mass. So we're doing estimations. So we make the estimation that the entire Earth, we're just trying to get the right order of magnitude, basically. So the entire Earth is covered in water, basically, because about 2/3 of it is. So that difference isn't going to make much of a difference. So we have to find, where is my cursor? There it is. The volume of this thin sphere or this thin shell covering the Earth. So that is going to be approximately pi or actually 4 pi. It doesn't have the 4 in the textbook, but I'm just going to add this in, times the diameter, or oh yeah, it's just pi times the diameter squared, because this is the diameter, not the radius. That's going to be the surface area times the depth of the ocean. So this is kind of a, yeah, this is kind of a cop-out answer, because the real value is going to be, or the real math that you would do is going to be pi times, or 4/3 pi r cubed is going to be equal to the volume of a sphere. So it's going to be equal to volume of the outer radius of the sphere minus the volume of the inner radius of the sphere. But because this little d, this diameter of the sphere, is so much smaller than the depth of the oceans, it's going to basically be constant throughout. So if you have a constant area, if you're talking about like a cylinder or a rectangular prism or anything like that, where you have a constant area for the volume that you're looking at, then it's just going to be that area times the height of the cylinder or the prism, or in this case, the depth of the ocean. So that is very, very much not great math, but it is a good approximation. Did you learn Taylor series in your calculus class?
I don't remember that one.
Okay. Yeah, so it's something that we're going to talk about. We're going to glance over it briefly later, but what this is actually is a Taylor series, which is a way that you create an infinite series. So V equals A1 plus A2 delta X delta R plus A3 delta R squared plus so on and so forth. So if delta R is really small, then the higher orders that you get are going to disappear. So you only have to worry about this term. So it's just a math thing. That's the actual explanation for why you're able to do this, but this is a good enough explanation for why you're able to do this. So I would just worry about this explanation and not the Taylor series explanation.
Professor?
Yeah.
Is that a P next to V after M equals
Oh, that is the Greek letter rho.
rho?
So that is going to be that is the unit, or that's the variable that we generally use for density. So and then since we know, so all that's left to do now, the only thing that we need to know, we have pi d squared. We need to know the depths of the ocean. We know that the maximum of the depth, we're going to do all, if all else fails, bound it. Then the maximum value of the depth is going to be equal to 3 times 10 to the third meters. That's just something we know experimentally, like we've been around the sea plenty of times. So we're going to assume that the average value of the depth is, I don't know why they're doing this exactly. It's going to be 3 times 10 to the third meters to the 1/2 power, so the square root of that. Which is going to, with meters on the outside, because like we said last time, you can't put meters on the inside of an argument. So we're just assuming that the average value of the depth is about the square root of the maximum value of the depth, which is, I'm not sure where they came up with that, but when you plug this in, it gives you pi d squared times d is equal to 9 times 10 to the 17th meters cubed. So that's about the depth of the ocean, or that's about the volume of the ocean. And then mass equals rho v. You do math, you do algebra. We've done this before. Which is equal to 9 times 10 to the 20th. Kilograms, because it's just rho times v. So it's just 9 times 10 to the 17th times 10 to the 3 kilograms per meter cubed. So it's 9 times 10 to the 17th times 10 to the 3, which is 9 times 10 to the 20th kilograms.